Good morning, everyone. I'm excited to welcome you to today's presentation. We'll be discussing the protection and optimization of Zamil PMY-840 package units using the DDC control panel. The focus will be on key components like the compressor, fan, pressure, temperature, and phase monitoring. Over the next few slides, I'll walk you through how these systems work together to ensure efficient and reliable operation. Let's get started. Today, I want to talk about the main objective of this upgrade. Essentially, our goal is to integrate a direct digital controller, or DDC, as the primary control system for both Zamil PMY-840 units. The DDC is a critical component because it offers real-time protection and monitoring. It can automatically shut down equipment if unsafe conditions are detected, helping us prevent potential damage or failures. By implementing the DDC, we're not just improving safety. We're also extending the lifespan of the compressors and fans, which means fewer replacements and maintenance costs over time. Plus, it enhances energy efficiency through smart sequencing and logic-based operations. This means the system makes intelligent decisions to optimize performance and save energy. And to tie everything together, think of safety as a function of sensors, logic, control, and feedback. When these elements work together seamlessly, we create a safer, more reliable, and more efficient system. This upgrade aligns perfectly with our overall goal of improving system performance and safety through advanced automation. Let's take a closer look at the DDC system overview. The DDC, or Direct Digital Control System, is essentially a programmable microprocessor that manages various building systems. It works with input and output modules that receive signals from different sensors, such as temperature, pressure, and electrical sensors. These signals are critical because they provide real-time data about the environment and equipment status. Based on this data, the DDC issues control commands to equipment like compressors, condenser fans, and alarm circuits. The key here is that all these actions are driven by programmed logic, allowing for precise and automated control. Another important feature is that the system can log data and record trends over time. This helps us analyze performance and make informed decisions. It also has the capability to automatically restart units once safe conditions are restored, ensuring continuous operation without manual intervention. Looking ahead, this system is designed for future integration with the Building Management System, or BMS. This can be achieved through network communication interfaces, which are outlined in Zamil's technical offer. This connectivity enhances overall system efficiency and allows for centralized management. So, in the context of our overall theme, this DDC system forms the backbone of intelligent building control, making operations safer, more efficient, and easier to manage. In this slide, we're focusing on the protection functions of the DDC, which are crucial for safeguarding the equipment. The DDC constantly monitors key parameters to prevent damage to compressors and fans. For example, it detects phase failure and voltage imbalance using phase monitors, and if these issues are identified, it will shut down the compressors to avoid motor burnout. It also responds to electrical issues like overvoltage or undervoltage by cutting the compressor circuit, which helps prevent stress and potential failure of the motor windings. When it comes to refrigerant system protection, low-pressure signals trigger an immediate stop of the compressor to prevent operation under insufficient refrigerant, while high-pressure signals cause a lockout to avoid overpressure damage. Temperature sensors on the discharge line play a vital role. They stop the compressor if temperatures exceed safe limits, protecting the system from overheating. Similarly, current sensors monitor fan motors. If overloads or failures are detected, they trigger alarms or shutdowns to prevent further damage. Differential pressure sensors help identify filter clogging, and they delay the start sequence to prevent coils from freezing, which can cause serious operational issues. Lastly, the DDC continuously checks the entire communication and sensor system, raising fault alarms whenever a malfunction occurs. An example of a protection formula is delta equals P high minus P low. If this pressure difference exceeds a set limit, the system will trip the compressor to protect the equipment. Overall, these protection functions are designed to keep the system safe, reliable, and efficient, aligning with our goal of maintaining optimal operation and preventing costly repairs. Now, let's take a closer look at how the integration with the Zamil PMY-840 works. Each PMY-840 unit already includes essential mechanical protections, such as high and low pressure switches and thermal sensors, which are crucial for safeguarding the system. However, the real advantage comes from the DDC, or Direct Digital Controller, which consolidates all these signals into a single, coordinated logic system. This means it receives a variety of inputs, analog inputs like suction and discharge pressures, compressor current, and coil temperature, as well as digital inputs such as high pressure, low pressure, fan status, overload, and phase condition. By gathering all this data, the DDC can make smarter, real-time decisions to control the system more effectively. The outputs from the DDC then regulate critical functions like starting and stopping the compressor, adjusting fan speeds, and even triggering alarms when needed. An important feature is that the DDC automatically alternates between the two units, which helps to balance their operating hours. This prevents uneven wear and extends the overall lifespan of the equipment. Connecting these points back to our overall theme, this integration highlights how modern control systems not only improve safety and reliability, but also optimize performance and longevity for our HVAC solutions. On this slide, we're looking at the control logic and sequence that keeps our system safe and efficient. The DDC, or Digital Device Controller, continuously monitors all the sensors, so that's temperature, pressure, voltage, and current. It's always checking these parameters in real time to ensure everything stays within safe limits. If any of these parameters go beyond their safe range, the system responds immediately by activating an alarm to alert operators and shutting down the compressor to prevent damage or failure. This quick response is crucial for protecting the equipment. Under normal operating conditions, the control logic starts by turning on the fan first, which helps with cooling. Then it starts the compressor. Throughout the operation, it keeps an eye on performance metrics to ensure everything runs smoothly. All events, including normal operations and any faults, are logged. This logging is vital for maintenance and for operators to review what's happening during each cycle. To give you a clear example of the logic at work, if the high pressure exceeds its limit, or the low pressure drops below its limit, or if the phases aren't balanced, then the system will stop the compressor immediately and activate an alarm. This logical approach helps us prevent potential damage and maintain system safety. So overall, this control logic forms the core of our system's safety and operational reliability, making sure everything runs smoothly and safely. Installing the DDC panel offers comprehensive protection for the Zamil PMY-840 compressors and fans, which is a key benefit. It helps prevent both electrical and mechanical failures, ensuring the equipment runs smoothly and reduces downtime. By balancing the operating time between units, it also promotes more evenly distributed wear and tear, extending the lifespan of the equipment. Another important advantage is that it reduces the need for manual resets, saving time and effort for operators. With real-time monitoring, operators can keep a close eye on system performance, allowing for quicker diagnostics when issues arise. Additionally, having accurate fault history helps in troubleshooting and planning maintenance more effectively. Overall, these benefits translate into longer equipment life, lower energy consumption, and significant savings on maintenance costs. All of these improvements align with our goal of optimizing operational efficiency and reliability in your systems. Now, let's talk about the implementation and handover process. The project execution follows Zamil CoolCare's approved procedure, which starts with an initial site survey to assess the specific requirements. Next comes the DDC installation, where we set up the control systems, followed by programming to ensure everything functions as intended. Then, we conduct thorough testing to verify performance. Once all these steps are successfully completed, We present the system to the client for functional tests, which will be witnessed directly by you. After a successful commissioning, we prepare and submit a detailed technical report. When everything is approved, we proceed with the handover. At this stage, the system is officially handed over to your operation team for daily use. It's important to note that while we handle the installation and commissioning, future maintenance remains your responsibility. If you look at the timeline diagram, it visually represents these steps, starting from the survey, moving through installation, programming, testing, reporting, and finally, the handover. This structured process ensures clarity and smooth transition from project completion to your ongoing operations.